Okay, so having seen what a JK flip-flop is, let's look at one of the applications of the JK flip-flop, and that is as a counter. What is a counter? It's a circuit which, depending on its input, will count how many inputs have gone. So, for example, uh, suppose you have a door with a radio transmitter on one side and a radio receiver on this side. Then every time that a person walks through this door, the signal gets interrupted. So let's say whenever the signal gets interrupted, you're sending a pulse. And then when there's no person going, it's 0. And when a person enters, you get a 1. So in the end, at the end of the day, if you want to find out how many people have entered this room, then all you want to do is you want to count how many pulses have gone through. So for that, we use what is called a counter circuit. So let's see how you can implement that using JK flip-flop. So the circuit diagram looks something like this. Let's see. Okay, so we are making what is called a 3-bit counter, and in order to make a 3-bit counter, we are going to use 3 flip-flops. So I'm calling these ones I'll call QA bar. So this needs 2 inputs. The input that I'm going to give it is some high input. So let's call it plus VCC. All I mean by that is J and K are always 1. And I'm going to send a clock pulse over here. But I'm going to make it negative. I'm going to get the complement of that. So this clock is basically your pulses. This is what you want to count. And then I put the next flip-flop, JK. Let's call this QB bar. And yet another one, JK QC bar. Each of them gets J and K 1. However, for each of these flip-flops, the clock comes from the previous output. So QA negated becomes the clock for this one. QB negated becomes the clock for this one. And in the end, what I'm interested in is QA, QB, QC. These are the outputs that I want. So as we saw, J and K are always 1. So it's only when A changes its state is when a pulse will go to the B, to the second flip-flop, and then when QB changes its state, that's when an input is going to go to the clock of the third flip-flop. So B is not going to change its state before A changes its state. C is not going to change its state before B changes its state. So in the end, the output of this circuit looks something like this. Suppose my clock looks like 1, 2, 3, 4, 6, 7, 8, 9, 10, and so on. So if this is what my clock looks like, then the output of A, basically whenever the clock, as we have seen before, every time the clock is on the falling edge, that is when your A gets triggered. That's when A changes its state. So So here the clock is falling, so A changes from 0 to 1. Here A is falling again, so once again A changes its state. And now this becomes a trigger A becomes a trigger for B. So now whenever A is falling, B state will change. So B looks like this. And C gets triggered by B. So C looks like this. Now every up state is 1, every down state is 0. So what you can see from here is that if I take the digits C, B, A, this exactly counts how many pulses have gone through. So if I'm labeling the pulses as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, you will notice that CBA over here, C is 0, B is 0, and A is also 0. Why is that? Sorry, maybe I should start labeling these pulses from 0, not from 1. Oops. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So 0, 0, 0 is binary for 0. Over here, you will see this is 0, 0, and this is 1 because this is high. Then over here, this becomes 0, 1, 0, and so on. For any number, you will find that. So this, for example, is 1, 1, 1, which is binary for 7. So if you look at the output of CBA, that gives you the binary representation of how many pulses have gone through. So this is a counter circuit. The next thing that we look at is a variation of the JK flip-flop. Well, not a variation, it's an extension of the JK flip-flop, and this is called the JK master-slave flip-flop, or sometimes abbreviated as the MSFF. What does this look like? So again, we start with our basic RS flip-flop, and its inputs are coming from a NAND gate. JK. There is a clock pulse giving one of the inputs to the NAND. From the output of Q and Q bar, we are going to two more NAND gates, and these also will get an output from somewhere. And that somewhere is basically the same clock, except you put a NOT gate over here. So you're sending the negative pulse of the clock that you have, not the negative, the complement of the clock of this first flip-flop. And this goes to the second flip-flop. And then we take feedback going to the original NAND gates. So this thing is called a JK master slave flip-flop. There are two flip-flops over here. If you look at it, this entire thing is like one JK flip-flop. This entire thing is like another JK flip-flop. The first one is called the master, and the second one is called the slave. How does this fellow work? When the clock is 1, it's in the high state. The clock of the second one is in the low state. So how should I call this? Let's call this 1 and let's call this 2. So the clock for the first one is 1. Then clock for the second one is 0. And if the clock for the second one is 0, then S and R are both going to be 1. And when S and R are 1, you know that the state doesn't change. So slave does not respond to whatever the master has been doing. Means basically the input that is coming from the master doesn't matter. The slave is not going to bother because its clock signal over here is 0. Now when clock 1 is on its falling edge, so it's just decreasing, now you will notice that the S and R for the master flip-flop become 1. So now Q and Q bar of the first flip-flop don't change. So Q bar of master remains same, maintain the previous state. But now clock 2 is increasing. So now the slave flip-flop is ready to take the input from the master. So it takes the previous state QQ bar which our master has left intact, and then it responds accordingly. So slave responds to previous state of master. And of course, when clock 1 is 0, so when it's now clock 1 bar, so or clock 2 is 1. So now the slave is going to retain its state. So, or should I say, no, since clock 1 is 0, the master does not respond to what you're doing to J and K. To the original J and K. So in this kind of setup, what the slave is doing depends on the clock pulse, and it depends on what the master flip-flop is doing. So one very useful example. So okay, no. So what we have seen over here is that initially the slave was doing its own thing. The master got some input. In the next step, whatever the master had, that input then goes to the slave, and now the master is not doing anything. So this is used in what is called a shift register. So you can think of a shift register as being a series of master-slave flip-flops. Let's see what the circuit looks like. This has, let's take 4 of these. Let's call them S1, R1, S2, R2, S3, R3, S4, R4, and then Q1, Q1 bar, Q2, Q2 bar, Q3, Q3 bar, Q4, Q4 bar, and of course each of them also has a clock over here. So we just set the output of each one as the next input. And over here, S1 and R1 are complements of each other. And there is also a common clock for all of them. Okay. So again, as a function of time, if the clock goes 1, 2, 3, 4, 5, 6, 7, like this. And of course, your S1 is your external input. So these are both inputs. And suppose S1 involves 2 pulses. 1, 2. Then what happens to S2? Well, or let's give them some names. No, let's call this A, B, C, D, and so on. So what happens at A is that so this has shifted by one spot. Why? Because first the master gets a state from the previous input, from the previous output, and then in the next step it passes it on to the slave, and then the master stops responding. So this pulse gets shifted one step to the right, this step also gets shifted one step to the right. Then if you look at B, now the third one acts as the slave of the second one. So exactly in the same way, this again gets shifted one step to the right. And then if you look at C, then this will again get further shifted one step to the right. And then if you take the output at D, similarly one more. So this is the kind of circuit that you want to use if you have a pulse S1 which you want to keep moving one step at a time. Where would you use a circuit like this? So you've seen those LED boards which have like an array of LED lights. And based on which LED lights are lit up, you can have some kind of birthday, like a birthday sign or something, some message that's written over there. I don't know, let's say these ones are lit. So it says hi. I don't know if you can read it, but then in the next step this hi kind of scrolls away to the left. So those scrolling lights that you get, that you can model using this kind of shift register circuit.